I'd like to introduce you to the concept of topology and how it relates to different GIS file formats. If you put yourself in the shoes of somebody who is designing a GIS data file format, so literally you're sitting there saying to yourself, okay, I need to find a way to store GIS data in a file. How would I do that? What are the kinds of decisions that I might make in order to be able to do that well? So really what this is about is getting you to understand the differences between different file formats, and when you're choosing one of them, what are the implications of that choice? Or if you're getting data from somebody else that's in a particular file format, that you understand the implications of that. So if you get something in a shapefile, that means that certain things may or may not have been done in terms of the data quality versus, say, in a coverage or a geodatabase. We'll cover all of these things as we go along, but the whole idea here is that I want you to kind of think about, you know, if you were the one that was kind of designing this file format, what is it that would be important to you? So first of all, if you think about like what would be useful, if you're creating, digitizing points, lines, or polygons, then ideally you want to try and prevent editing errors from occurring to begin with. And if they do occur, then you want to be able to detect them and correct them easily. So these might be errors like things where, you know, things don't line up exactly the way they should, or there's an overlap where you didn't really want one, things like that. It may also be that you're trying to find ways of storing data more efficiently so that there's no redundancy in the data. In other words, that you're not storing the same data in two different places or twice when you don't need to. And so that would be more efficient in terms of storage. And then in terms of using the data, you want something that's easy to edit and that makes spatial analysis more efficient. So for example, is this road connected to that road? If you wanted to be able to do, say, network analysis for driving directions, you want to have the software be able to easily recognize where lines are connected to one another to be able to say, oh yeah, I could turn from this road onto that road, and so on. So this brings us to the concept of topology. And I'm just going to start with a couple of definitions to help us sort of figure out what this is, and then I'll kind of illustrate it more as we go along. So one, you know, literally kind of textbook definition is the branch of geometry that deals with the properties of a figure that remain unchanged even when the figure is bent, stretched, or distorted. So if we have a little figure like this, we have a couple of polygons. You'll notice, for example, that there's a corner point here and a corner point there in relation to, between the purple polygon and the magenta polygon. So if this is stretched, you'll notice that topologically, those are still in the same position relative to one another. In other words, they didn't change, there wasn't a gap that was introduced, that kind of thing. So if you think of that in terms of any polygons, points, lines, the topology of that is if you warped it in some way, say you were doing some kind of correction to it, or something got distorted, or you reprojected it, then the coordinates that store the actual locations of those points may change. But topologically, the relationships between those things don't change. That's really what topology is about. A more pragmatic definition that is given in the Esri dictionary is that topology defines and enforces data integrity rules. And that, I think, is a more pragmatic way in terms of us as GIS users of thinking about what topology is good for and why it's useful for us to know about it. So, for example, there should be no gaps between polygons. So from a user point of view, when you're creating a data set or you're cleaning up a data set, trying to find errors and correct them, you can impose rules on that data set to say, for example, you don't want to have any overlaps between polygons. And if you can do that, if you can set up these rules, then that's a form of topology that you're able to then check to see if those rules have been followed and correct them if needed. So for example, if we have two polygons here that represent two parcels of land, the whole idea is that you have one owner per parcel. You can't have overlapping parcels like this. So if we move these apart, you'll see that the magenta polygon is actually overlapping the purple one. And we can't have that. The whole idea is that we have one record per parcel that represents one owner. So we don't want to have overlap. So if we could impose a topological rule that says we're not allowed to have overlaps, it would detect those kinds of things so that we are able to correct them. So we can only have one landowner. And so what we could do, for example, is cut out the notch from the purple one so that we only have one landowner. Now, we could have done it the other way around. It all depends on who owns that land as to what's the most appropriate way to do it. I'm just illustrating the fact that you can do it and that the topology helps you to identify those things. And this brings us to the concept of planar enforcement. All that means is that all space must be occupied and by only one polygon. So everything is accounted for. We have no parts of our study area, if you want to think of it that way, that have gaps where there's no polygon. You don't want that. And you also don't want to have areas where there's overlapping polygons. The whole idea is just you have one polygon for any particular location. That's planar enforcement. Topology can also help us with other kinds of things like detecting adjacency. So it's a common kind of spatial query or thing that we want to know is if we have selected a polygon or there's something we want to analyze, what polygons are adjacent to it. And if we want to, depending on which data file format we use and how we set things up, we can have that information stored in the data set. So it's very easy for the software to be able to determine that polygon B is in fact adjacent to polygon A. Another topological thing that we can check for is containment. So often we want to know, which thing is inside another thing. So for example, here is the water polygon inside the land polygon. And so that with a topological rule, you could set it up so that that is built into the file. So again, it makes it easy for the software to be able to detect that. And you'll notice here that because of planar enforcement, that water polygon is not on top of the land polygon. It's actually cut out that section of the land polygon so that we only have one thing at one location. Another common thing we want to detect are slivers. So when you're digitizing, it's easy, especially if you don't set up snapping correctly, things like that, to have these very small little areas that are gaps or overlaps between our different areas. So for example, here, we have a tiny little overlap or sliver between the purple and the magenta polygons. So which one of those is correct? That is fairly likely that wasn't intentional. That wasn't the way we actually wanted it to look. That's a mistake that we want to be able to correct. Same thing here is that we have an area where there's a gap that's not supposed to be there. So again, with planar enforcement, we want to be able to correct for these things. So depending on how we set things up, if we use topology, we could actually correct for these things, get rid of all the slivers, the gaps, overlaps, and so on, so that we have a much better looking version of the data. Another concept related to this is data redundancy. So if I actually move these polygons apart from one another, you'll see that, for example, this area here, that border is stored twice, right? Same thing with this one here and this one. So you're storing the lines that define these polygons twice. So why is that a problem? Well, there's a couple of reasons. One is that you're storing that data more than once, so it's redundant. It's taking up more space in our database than we want it to. So why do that if it's inefficient? We want to avoid that. So that's one thing. But I think a more important thing is imagine if that boundary has to be changed or edited for some reason. So maybe it has to be shifted. Maybe something's happened. The boundaries move for whatever reason. So if you have stored those lines twice, that means you have to edit them twice. So that takes up more time. And it also means there's an opportunity for an error to be introduced, because what if you don't move them exactly the same way both times, so that you've introduced some kind of sliver, overlap, whatever. So it's one of those things where it may seem like a small detail, but depending on what kind of data you're working with and how important this could actually be a big deal, is you want to be able to avoid these kinds of editing errors from occurring to begin with, or being able to correct them after the fact. We can also look at topology in relation to lines. So imagine that these lines represent roads. Here we have a main street and we have a road connecting to it. That's great. That's the way we wanted it to be when we created it. But what if we have a situation like this where they're meant to meet at this intersection, but there's been an overshoot, as we would call it. So that was not the way it was meant to be, but that's the way it was digitized when it was created. So we would call that an overshoot. So there's a couple of ways that we could deal with this. While we're editing, while we're creating this data, you can set what's known as the snapping tolerance, so that anything that's inside, say, that red circle would actually automatically be snapped to or moved to the closest existing point. So if we had a point where that other line exists, then if it's inside the snapping tolerance, it would automatically be moved to that location. So it would avoid that overshoot to begin with. If our snapping tolerance wasn't set properly, or we weren't using snapping at all, then that's something that we could detect after the fact through a topological rule. And here's another situation where we have a line that's meant to meet at the intersection but still doesn't. But in this case, it would be called an undershoot because it didn't quite make it to the other line, and it's actually outside the snapping tolerance. In other words, the gap between them is larger than the snapping tolerance, and so it wasn't automatically snapped to it. And depending on how we set up the topology, it still might not be detected. It all depends on how you set these things up. So this would be an error beyond the snapping tolerance. So if we're still looking at roads here as an example of lines and topology, a very common thing, of course, is that we want to look at things like driving directions. Now, if we want to do something like that, then it's really important for us to be able to detect where these lines intersect. Like, it's not all about roads, but this is a good example, I think, is that you want to be able to store in there the fact that these lines meet at the roads. So this is an idea of topology that we're going to look at. If we didn't have topology, then those lines would not be aware of each other. They would just sort of think of it as they would lie on top of each other, or they exist kind of separately in space, and they don't know that they're connected to each other. But if we institute a topological relationship through our data in one form or another through different file formats, then we can build that into the data set so that it knows that these lines are connected, and that makes it much more efficient to be able to do things like navigation and driving directions, things like that. So just to summarize, some of the basic topological relationships, things like adjacency, containment, connectivity, these are examples of topological relationships that we would like to be able to detect and use for various things in terms of data creation, creating better quality data, and then making our analysis more efficient. There are other topological relationships. These are just sort of the most common ones. So why use topology? Well, I'm hoping that it's becoming fairly obvious now why it's a good idea. We want to be able to reduce errors in our data set. We want to have more efficient data storage, and we want to have more efficient analysis.